this little topic's about finding the points of intersection of lines, but using it from a vector sort of idea. We've done a lot of intersection of lines in the past, and it's often used for the simultaneous equations, finding that sort of stuff. So we're really doing a very similar thing. But when we're using vectors, we just got to consider what the vectors mean. All the questions in the textbook are only 2 dimensions, which makes it easier in some ways to write the question, and that's what I'm going to get you to afterwards, is have a go and see if you can come up with lines that are definitely intersecting. Because if you think about a 3-dimensional space, 2 lines may very well never actually meet. If they're offset by whatever. In fact, if you think about it, it's actually very unlikely that they're going to meet. The chances of getting them to meet is small. So to actually write a question that has them meeting means that you had to know that they were meeting in the first place, which means you probably have to work backwards. So after we had a quick look at this, I actually want you to have a go at that. I want you to come up with a question almost by finding 2 lines in 3-dimensional space that intersect, and then think, how could I write that question so that it was find where these 2 lines meet? Okay, so it's sort of like the backwards way, and if you can do that, that helps with the understanding of it. But we'll start with this one. All the questions from 6F which are about this have a context that is sort of based on like showing that 3 points actually make an equilateral triangle. In this case, it says in part C that it's going to be an isosceles triangle. I'm not going to do the whole question. Okay, you can work on some of that stuff. I just want to quickly go through the process of how can you show or how can you find the points of intersection. Okay, so this question says we've got 3 lines and the vectors that describe those lines, or the vector equations for those lines, for A to B is written there, A to C is written there, and B to C is written there. It says to draw the lines accurately on a grid. I'm not going to worry about that, but the part that we're going to look at is finding the coordinates, and let's just find the coordinates of A. So we're going to try and find what the coordinates of A must be. So the 2 lines, obviously, that we're going to use are the lines that represent A to B and A to C, and they just have to be equal. What I want to point out, though, one thing that's really important, is if we look at these 3 sets of vector equations up the top, notice that the little parameter that's used, they use a different letter each time. It's really important that when they're different lines, but you're using them in the context of the same question, that parameter will, they're not equal parameters. They can be different, okay? What we're actually trying to do is sort of work out what those parameters would be to make it so that you get the same point or the same coordinates for it. So we're looking for point A, so we're going to use the A to B and the A to C, so the top 2 ones, and effectively we can just write those, if I write them, they're X and our Y, so X, Y, we want that to be the same for both. That's the whole point of getting 2 points the same coordinates. So really, we're just equating the A to B one, which is -1, 6, plus R, 3 minus 2, must be equal to 0, 2, plus S, 1, 1. That must be true, because then that's when the X and the Y are exactly the same. That must be where they meet. Okay, and so we then just want to pull it out of the vector equation and write 2 equations from it. Okay, so from our left-hand side, we know that the X, to do with the X, is -1 plus 3R, okay, but the other X coordinate is 0 plus 1 lot of S, so it just equals S, okay. That is our first equation that must be true. Second one is just 6 take 2R must equal 2 plus S. That's our second equation. Okay, and then just solve these simultaneously, so nothing different. So your choices are yours. The book, I think, in their example, uses the elimination method, lines them up and uses the elimination method. Perfectly okay, but hey, you're going to have a calculator. Just line them up. I would rewrite this as being the first one. Let's make it 3r and take s is equal to 1. And the second one is negative 2r, take s, and that's equal to negative 4. Okay, so if you write it in that style, it is the style you'd do the elimination method. It is actually useful because we are going to start doing some work putting them into sort of matrices from this soon. But at this point, that's just perfect for putting in the calculator. So it's easier to do that. And I would suggest, if I was doing that as a question, I would use the calculator to solve them. But I haven't got that in front of me. So the elimination method just means, well, if I have minus s and I take away minus s, I get 0. So I'm going to take this line. Okay, so it becomes 5r is equal to 1 out of, so it's 5, so therefore r is equal to 1. Okay, and I could plug that back into either of my equations, and I know from up here, oops, is that going to disappear? Yes, I've got s is equal to minus 1 plus 3r, so probably a good spot to put it in. So sub into the original version of 1, s is equal to minus 1 plus 3 lots of 1. So what's that? Minus 1 plus 3 is 2. Okay, so s is equal to 2. The final thing to do is to say, well, what am I trying to find out? That's giving me what the r and the s must be when they meet, where the 2 points meet. So I just need to substitute them into my 2 equations to work out what x and y coordinates they are. If I've done everything right, I really only need to sub into one of them because it should be the same for both. Perhaps it's worth doing a bit of a check on that. But our first one, our x, y, so our x for the first one is equal to minus 1 plus 3 lots of r, which is 3. Okay, so that's equal to 2. All right, that's from the line A to, is it A to B, the first one? I assume it is, yep. So if I use AB as an example here, and I can do AC as the other example, then y is equal to 6 minus 2 lots of 1. Okay, so it becomes 6 take 2, which is 4. So that tells me that they meet at the point 2, 4. I should get the same result if I do the other line. So x equals 6. Sorry, that's the wrong one. X equals 0 plus s, which is 2. Right, which is equal to 2. That's good. And y is equal to 2 plus also s, which is 2, which equals 4. So you get the same point, which we'd expect if they meet. Okay, so that's the process of finding the the coordinates of where they meet. Okay, like I said, all of the, I mean, that doesn't solve the whole question there. All of these are in a set of questions which say, okay, we'll work out the other 2 points and then use some sort of method to prove that it's an isosceles triangle. Okay, now we have stuff from previous topics to look at. You could, if it was isosceles, looking at the lengths of the sides, okay, but also angles you could work out. You could do some proving like that. So whatever works out to prove it, okay, that's something you can have a go at. Once you know it's isosceles, you could use some vector methods to prove your answers to part B2 if you like. Okay, but the most important skill just at the moment is just finding the intersection of those points. So have a go at them, but before you do that, I want you to then have a go at coming up with a question, and it doesn't have to be like this, just a question that says find the point of intersection between, but I want you to do a question. I want you to make it so that the point of intersection gives integer values. Okay, so don't do it so that it just has these horrible fractional points of intersection, but three-dimensional. So you cannot just randomly make up, two three-dimensional lines. Well, you could, but the chances that they will actually intersect is really small. Okay? What I want you to do is think, okay, how can I write two different three-dimensional lines that will intersect at a known point? Work that out, and then just write the question as, okay, find the point of intersection between these two lines. Once you've got that, swap it with someone, see if they can solve it. So don't tell them what the point of intersection is, see if they can actually get that. Now, why? Because the chances are you can get a question like that in the test. The textbook hasn't written any, in this section anyway, on three-dimensional lines. Okay, partly because it's a bit of a pain, I suppose, because you've got to go through a process of doing it.
Ask you to construct the question?
Could they? They're probably unlikely to ask you to construct a question in their... absolutely not likely to do it in the exam because it'd be too hard to mark, because then you'd have to check every one individually, and people are too lazy to do that and they've got time. The reality, I could say, oh yes, I could do that in test because there's only 6 or 7 of you, but I'm not going to. So I'll tell you right now that I'm not going to ask you to construct a question in the test, but it's a good practice because it'll make you think about the processes and how things relate. So have a go at it, see what you come up with.